Good morning, everybody, and welcome back to Next Door NetAdmin. Now, last time we were talking about ZFS, I went into a good bit of detail on vdevs and pools and sort of an explanation of how the physical side of ZFS works, how you set up your disk array or pool, as ZFS calls it, into a cohesive whole. Today, I'm going to continue on that thought, but instead of looking at the physical side, we're going to take a look at the logical side of things. And we're going to just jump right in and start talking about datasets. Now, when you create a section of your pool to store data in, there's a couple of different ways you can do it. You can generally do it as a dataset, or you can do it as a Zvol. The difference between those, we'll talk about it. When you create a dataset, it's similar to creating a partition in concept. It's a set space on the disk where you can set parameters like quota, which sets a maximum amount of data that dataset can contain. You can set a reservation, which sets up a minimum amount of space that the dataset will hold, so that you know that you've always got a minimum amount of capacity there. Now, I'll explain a little bit more about that because reservations are not a concept that is frequently used in my mind, and it'll become more important when we get to the Zvols. You can set compression on a data set, and in fact, it's encouraged to do so. The default type of encryption, LZ4, is very, very fast and reasonably good. So you can actually store more data on your pool than you otherwise would be able to, with no observable performance cost for the most part. So it's a good thing to have. You can enable deduplication, so that if you write the same file over and over in different places in the file system, it'll only store one copy of that data. However, deduplication has a very large cost in RAM and in processing time associated with it. So it's recommended not to enable that unless you've specifically built a system for the purpose of doing that. You can enable encryption. In more recent versions of OpenZFS, you can enable encryption on the dataset directly without relying on some sort of full disk encryption scheme underneath it. But you have to set up encryption at the time of dataset creation. You can't go back and add it later. It's either on from the start or not on at all. That's just how it is. So there are a lot of options that you can configure on this that make it something like a partition. And yet in concept, it looks and behaves a lot like a folder. It mounts into a particular section of your file system. And from there, you can even create sub-data sets that appear as other folders underneath the first data set, even though it's completely different and can have completely different options associated with it. And you can do a lot of other interesting things with your data sets, like choose where it appears. It doesn't all have to be under the same directory, even if it's all under the same root data set. Here's an example. On a TrueNAS core system, it's very common to have a pool called tank. It's a tank full of water, essentially, a tank full of storage space. And your data sets will typically be created under that. So you'll have tank/files, tank/videos, tank/whatever. But it doesn't have to be mounted there. If you really, really, really wanted to, and you shouldn't do this on a TrueNAS system because the operating system isn't set up to recognize this, but if you were running a different system, let's say one where you were in full control of everything that you were doing, there's no problem with deciding, you know what, I don't want videos under /tank. I want videos under /home/ my user. So you've got a ZFS dataset storing files that should be in your home directory, but it's storing it in the dataset that's in the pool called tank. You can do that. You can choose to put it on the same level. You can choose to move it around. You can basically put it wherever you want. Now, another good thing that you can do with your data sets is take a snapshot of them. Because of the way that ZFS works, where you have each block individually checksummed and the checksum stored at the block higher until you get all the way to the one block at the top, the super block. Because of the way that works, you can take a snapshot showing the entire file system all in one place. And the other feature that makes this possible, which I have not mentioned so far, is called copy on write, or COW. A file system that is copy on write does not overwrite files directly. It creates a copy. So when you update, you take this version of the file and you decide to update it, the update is saved as a separate copy. So the old block that had the old file data is still there, and the checksum is still saved in the super block of the previous copy of its parent, and et cetera, et cetera, et cetera. But the new copy will have a new checksum. The new checksum will be stored with the new copy of its parent, and you keep going that way. So in order to save a snapshot of the file system, all you really need to do is grab the super block, the one at the top, and its checksum will reference all the other blocks in their previous or current state. And then as you go forward, new versions will be created, a new super block will be created showing or linking, to all of the other blocks in its copy, its version of the file system. And so really the snapshot only takes up as much space as the changes. If you want to be technical about it, the new version, the current version of the file system, only takes up as much space as the changes that have been made since the last snapshot. But because of the way people look at the live file system as having all the data, 6 of one, half a dozen of the other. You can say the live system only has 300 megs when the whole thing is a terabyte, or you can say the snapshot only uses a unique 300 megabytes and the live system has the full terabyte of live current data. Either way you want to look at it, it means almost the same thing, even if technically it might be a little different. These snapshots are very, very quick to create, almost instantaneous, because all you have to do is take a quick, just mark this version of the super block as not going anywhere. It's associated to a snapshot, so that next time you want to overwrite it, you know that the new super block is part of the root file, the live, file system. I'm mixing up my words like crazy today. Isn't that fun? All of this is a data set. Cool. Within a data set, your file system is ZFS. Sure. But you can then expose this to other machines using other software. For example, if you were to use Samba, you can expose it using SMB, which is the Windows file sharing protocol, and Windows will be able to log on and use that. You can expose it using NFS, which is Network File System, which is much the same thing as SMB in intent, except it was developed for NIX variants, Unix, Linux, etc. So there are lots of different ways that you can deal with this. If you want to run an FTP daemon, you can. Go ahead, make it available over FTP. Make it available over SFTP and SSH if you want. Make it available over rsync. The choices are yours. It's just a file system. As a file system, you can also include other things. For example, Windows file share permissions under SMB tend to go way beyond the standard Nix permissions of read, write, execute. Windows has many more permissions, and you can set that up for different groups, different users, etc. So you can have extended ACLs in the file system where you can store all of these additional Windows permissions and Windows rights. That'll work. And then that's available to you over SMB. That's cool. But this is all for datasets, like I said. How about Zvols? A Zvol is a block device. Pure and simple. That means that ZFS doesn't know what files are on it. It doesn't even know what file system it is. It is just a section of the pool that has been set aside as a single block device. You hand that block device over to another machine and you can say, here it is over iSCSI, and it's a disk drive. It is a disk drive. Do with it as you wish. If you give it to Windows, Windows might format it as NTFS. If you give it to Apple, Apple might format it as APFS. If you give it to a Linux system, it might format it as XFS or ext4 or any of the other file systems that Linux can use. And ZFS doesn't have to know anything about it. It's just a block device. But, crucially, it still benefits from ZFS checksums, because every block of data, ZFS doesn't have to know what's in it. It doesn't have to know whether it's a file of some text format or whether it's video or whether it's pictures or whatever. It doesn't have to worry about it. All it needs to know is, I have this sequence of data, this is the checksum for it. And so it can still do the standard data corruption checks and resilvering and provide all of the protection and resiliency that ZFS offers even in datasets. You can have an encrypted Zvol. Same thing. It doesn't need to know what the data is. All it needs to know is, I have this stream of data, let's encrypt it. Okay, cool. We can do that. Compression, you can do that too. It's not as simple because unless you have a string of zeros, you don't necessarily know where one file starts and where another one begins. So you have to just compress the whole thing. I nearly said encryption again. I've got encryption on the brain today, apparently. You can just compress the whole thing. And LZ4 will still do a reasonably good job of it at very minimal impact, performance-wise. So it's still a good idea to enable it. But when it comes to snapshots, now we're talking something a little different, a little more involved. Depends on how you've set up your Zvol, your block device. I mentioned a reservation as an attribute that you can specify. If we go back to datasets for a minute, every dataset appears to have the full free amount of disk space available within the entire pool, because theoretically you could add that much data to that dataset. So your free disk space is the total free disk space of the entire pool. And as you add files to one dataset, you will see the amount of free disk space decrease on the other datasets, because they're essentially using the same free disk space. You can set a quota to say, hey, this is the maximum amount of data you can put in there. And that data set will see that quota. Everything else will continue to see the full size of the free disk space because they're able to use the full free disk space if they want. A reservation works in the opposite fashion. A reservation says, I'm going to take 5 gigs of space. That is the minimum space assigned to this particular data set. Nobody else can encroach on that. Everybody else can use everything on all the free disk space available up to the last 5 gigabytes. The last 5 gigabytes have to go to this data set over here. So all of your other data sets would see their free space decrease because you've got a reservation for this one other data set, and only that data set would see the full total of free disk space available to it. It's a little weird, but in a Zvol, by default, every device that you create, every Zvol block device that you create, has a set size. It has to have a set size because you're presenting this as a fixed block device, which means that you are in essence creating a reservation and a quota that are the same number, essentially. You've got a maximum amount that it can use, but you've also got a minimum amount of space that is reserved for this block device. Because if you present a block device to a Windows machine, let's say, every operating system will do this, but we'll go with Windows as the example. If you give it a block device and say, hi, here's a hard drive, it has nothing on it, it's yours to do with as you wish. You get halfway through it, and suddenly your disk drive that says, oh yes, I'm still 50% free, but I can't hold any more data. That does weird things that usually causes the disk volume to crash badly with lost data. Lost data is not a good thing. So to prevent that, you have to have your reservation set up to make sure that you've got the correct amount of disk space available that you've promised. Over-promising stuff that you can't deliver is called over-provisioning. You can do it if you want to, but by default, it won't. Where this comes in, so if you create a sparse volume, one where it's over-provisioned, and you say, oh yes, you have a full terabyte, and actually you've only got 200 gigabytes, and you're like, if it starts to get close to that, I'll just add more disks and make sure that eventually I can fulfill the full terabyte. You can run like that if you want. It's not generally recommended because those of us with a, more conservative mindset, technically speaking, will go, what if? If something goes crazy and you start writing data out, you may not have time to fulfill the provisioning. You might crash the machine that's trying to use this, which is a bad thing, but it's still there for you if you want to do it. And here's where it affects snapshots. If you take a snapshot of a Zvol, you have one version of an entire block device, 15 terabytes, let's say. And as soon as you have any new data, you're creating a new 15 terabyte block device, complete with the reservation, complete with the quota. Again, ZFS doesn't know what data is in there. All it knows is that this is a block device. And so every snapshot doesn't just use the change to data, the snapshot uses the full size of the Zvol for every snapshot. Ouch. If you have not planned for this, ouch. Especially when you're getting into large data sets, or large sets of data is what I should say to distinguish it from a data set. If you created your Zvol sparse, so that it doesn't have that reservation set, if you're living life on the edge, then yes, you can create a snapshot that will also be sparse, because rather than taking a snapshot of the entire block device, ZFS is only taking a snapshot of the data that has been written to that block device. Okay, so you can do that. But again, you can't set a snapshot to be sparse when the full live version is not sparse. The setting is the same for the snapshot and the live source, whether that's a data set or a Zvol. So that's some of the trade-offs there. These kinds of data stores work better in different circumstances. If I'm using a general file share to store user files, a data set is absolutely the right thing to use. Use that all day, every day. If you want to do something like hosting a hard drive for a virtual machine, that is better off in a Zvol because there's more compatibility for that. You can create an iSCSI volume, put the virtual machine's hard drive on that, give it to your virtual machine, call it a day. But then you have to take additional backup measures because snapshots will be a lot more costly, and you won't be able to keep as many of them as you would be able to on a data set. So it's something to think about. As is everything technical. Anytime you're dealing with this stuff, there's always stuff to think about. And there's lots of it. Lots of little bits and pieces. But then, that's where you get people like me. That's our job. That is probably more than enough detail on that for now. So thank you very much, everybody, for watching. If you have any comments or any thoughts or questions, feel free to leave them down in the comments. But until next time, I am your next door NetAdmin, and we'll see you next time.